In the last video, we talked about gradient descent for minimizing the cost function j of theta for logistic regression. In this video, I'd like to tell you about some advanced optimization algorithms and some advanced optimization concepts. Using some of these ideas, we'll be able to get logistic regression to run much more quickly than is possible with gradient descent, and this will also let the algorithms scale much better to very large machine learning problems, such as if we have a very large number of features. Here's an alternative view of what gradient descent is doing. We have some cost function j, and we want to minimize it. So what we need to do is we need to write code that can take as input the parameters theta, and that can compute two things, j of theta and these partial derivative terms for j equals 0, 1, up to n. Given code that can do these two things, what gradient descent does is it repeatedly performs the following update, right? So given the code that we wrote to compute these partial derivatives, gradient descent plugs us in here and uses that to update our parameters theta. So another way of thinking about gradient descent is that we need to supply code to compute j of theta and these derivatives, and then these get plugged into gradient descent, which can then try to minimize the function for us. For gradient descent, I guess technically you don't actually need code to compute the cost function j of theta. You only need code to compute the derivative terms. But if you think of your code as also monitoring convergence or some such, we'll just think of ourselves as providing code to compute both the cost function and the derivative terms. So, having written code to compute these two things, one algorithm we can use is gradient descent. But gradient descent isn't the only algorithm we can use, and there are other algorithms, more advanced, more sophisticated ones, that if we only provide them a way to compute these two things, then these are different approaches to optimize the cost function for us. So conjugate gradient, BFGS, and LBFGS are examples of more sophisticated optimization algorithms that need a way to compute j of theta and need a way to compute the derivatives, and can then use more sophisticated strategies than gradient descent to minimize the cost function. The details of exactly what these three algorithms do is well beyond the scope of this course, and in fact, you often end up spending many days or a small number of weeks studying these algorithms if you take a class in advanced numerical computing. But let me just tell you about some of their properties. These three algorithms have a number of advantages. One is that with any of these algorithms, you usually do not need to manually pick the learning rate alpha. So one way to think of these algorithms is that given the way to compute the derivative and the cost function, you can think of these algorithms as having a clever inner loop. And in fact, they have a clever inner loop called a line search algorithm that automatically tries out different values for the learning rate alpha and automatically picks a good learning rate alpha, so that it can even pick a different learning rate for every iteration. And so then you don't need to choose it yourself. These algorithms actually do more sophisticated things than just pick a good learning rate, and so they often end up converging much faster than gradient descent. These algorithms actually do more sophisticated things than just pick a good learning rate, and so they often end up converging much faster than gradient descent, but a detailed discussion of exactly what they do is beyond the scope of this course. In fact, I actually used to have used these algorithms for a long time, like maybe over a decade, quite frequently. And it was only a few years ago that I actually figured out for myself the details of what conjugate gradient, BFGS, and LBFGS do. So it is actually entirely possible to use these algorithms successfully and apply to lots of different learning problems without actually understanding the inner loop of what these algorithms do. If these algorithms have a disadvantage, I'd say that the main disadvantage is that they're quite a lot more complex than gradient descent. And in particular, you probably should not implement these algorithms, conjugate gradient, LBFGS, BFGS, yourself, unless you're an expert in numerical computing. Instead, just as I wouldn't recommend that you write your own code to compute square roots of numbers or to compute inverses of matrices. For these algorithms also, what I would recommend you do is just use a software library. So, to take a square root, what all of us do is use some function that someone else has written to compute the square roots of our numbers. And fortunately, Octave and the closely related language MATLAB, where we're using that, Octave has a very good, has a pretty reasonable library implementing some of these advanced optimization algorithms. And so if you just use the built-in library, you get pretty good results. I should say that there is a difference between good and bad implementations of these algorithms. And so if you're using a different language for your machine learning application, if you're using like C, C++, Java, and so on, you might want to try out a couple different libraries to make sure that you find a good library for implementing these algorithms, because there is a difference in performance between a good implementation of conjugate gradient or LBFGS versus a less good implementation of conjugate gradient or LBFGS. So now let's explain how to use these algorithms. I'm going to do so with an example. Let's say that you have a problem with two parameters, or theta equals theta 0 and theta 1. And let's say your cost function is j of theta equals theta 1 minus phi squared plus theta 2 minus phi squared. So with this cost function, the value for theta 1 and theta 2, if you want to minimize j of theta as a function of theta, the value that minimizes it is going to be theta 1 equals 5, theta 2 equals 5. Now, again, I know some of you know more calculus than others, but the derivatives of the cost function j turn out to be these two expressions down here. So I've done the calculus. So if you want to apply one of the advanced optimization algorithms to minimize this cost function j, so if we didn't know the minimum was at 5, but if you want to have a cost function, find the minimum numerically, right, using something like gradient descent, but preferably more advanced than gradient descent, what you would do is implement an octave function like this. So we implement a cost function theta function like that. And what this does is it returns two arguments. The first, jval, is how we would compute the cost function j. And so this says jval equals theta 1 minus phi squared plus theta 2 minus phi squared. So it's just computing this cost function over here. And the second argument that this function returns is gradient. So gradient is going to be a 2 by 1 vector. And the two elements of the gradient vector correspond to the two partial derivative terms over here. Having implemented this cost function, you can then call the advanced optimization function called fminunc. It stands for function minimization unconstrained in Octave. And the way you call this is as follows. You set a few options. Options is a data structure that stores the options you want. So grad on, this sets the gradient objective parameter to on. It just means that you are indeed going to provide a gradient to this algorithm, and we're going to set the maximum number of iterations to, let's say, 100. We're going to give it an initial guess for theta. This is a 2 by 1 vector, and then this command calls fminunc. This @ symbol represents a pointer to the cost function that we just defined up there. And if you call this will compute. We'll use one of the more advanced optimization algorithms. And if you want, think of it as just like gradient descent, but automatically choosing the learning rate alpha for you, so you don't have to do so yourself. But it will then attempt to use these sort of advanced optimization algorithms like gradient descent on steroids to try to find the optimal value of theta for you. Let me actually show you what this looks like in Octave. So I've written this cost function of theta function exactly as we had it on the previous slide. It computes jval, which is the cost function, and it computes the gradient with the two elements being the partial derivatives of the cost function with respect to the two parameters theta 1 and theta 2. Now let's switch to my Octave window. I'm going to type in those commands I had just now. So options equals optimset. This is the notation for setting my parameters or my options for my optimization algorithm. Grad option on, max iter 100, so that says 100 iterations, and I am going to provide the gradient to my algorithm. Let's say initial theta equals 2 by 1, so that's my initial guess for theta. And now I have op theta function val exit flag equals fmin unconstrained, a pointer to the cost function, and provide my initial guess and the options, like so. And if I hit enter, this will run the optimization algorithm. and it returns pretty quickly. Oh, this funny formatting, that's because my line, my code wrapped around. But so this funny thing is just because my command line had wrapped around. But what this says is that it numerically ran this, think of it as gradient descent on steroids, and it found the optimal value for theta is theta 1 equals 5, theta 2 equals 5, exactly as we're hoping for. The function value at the optimum is essentially 10 to the minus 30, so that's essentially 0, which is also what we're hoping for. And the exit flag is 1. And this shows what the convergence status of this. And if you want, you can do help fmin unc to read the documentation for how to interpret the exit flag. But the exit flag lets you verify whether or not this algorithm thinks it has converged. So that's how you run these algorithms in Octave. I should mention, by the way, that for the Octave implementation, this value of theta, your parameter vector theta, must be in RD for d greater than or equal to 2. So if theta is just a row number, so if it's not at least a two-dimensional vector or some higher than two-dimensional vector, this fmin unc may not work. So if in case you have a one-dimensional function that you need to optimize, you can look in the Octave documentation for fmin unc for additional details. So that's how we optimize our toy example of this sort of simple quadratic cost function. How do we apply this to logistic regression? In logistic regression, we have a parameter vector theta, and I'm going to use a mix of Octave notation and sort of math notation, but I hope this explanation will be clear. But our parameter vector theta comprises these parameters theta 0 through theta n, because Octave indexes vectors using indexing from 1. Theta 0 is actually written theta 1 in Octave, theta 1 is going to be written so theta 2 in Octave, and that's going to be written theta n plus 1, right? And that's because Octave indexes its vectors starting from an index of 1 instead of an index from 0. So what we need to do then is write a cost function that captures the cost function for logistic regression. Concretely, the cost function needs to return jval, which is jval, so you need some code to compute j of theta. And we also need to give it the gradient. So gradient 1 is going to be some code to compute the partial derivative with respect to theta 0, the next partial derivative with respect to theta 1, and so on. And once again, this is gradient 0, this is gradient 1, gradient 2, and so on, rather than gradient 0, gradient 1, because Octave indexes its vectors starting from 1 rather than from 0. But the main concept I hope you take away from this slide is that what you need to do is write a function that returns the cost function and returns the gradient. And so in order to apply this to logistic regression, or even to linear regression, if you want to use these optimization algorithms for linear regression, what you need to do is plug in the appropriate code to compute these things over here. So now you know how to use these advanced optimization algorithms. Because for these algorithms, you're using a sophisticated optimization library, it makes the code just a little bit more opaque, and so just maybe a little bit harder to debug. But because these algorithms often run much faster than gradient descent, often, quite typically, whenever I have a large machine learning problem, I will use these algorithms instead of using gradient descent. And with these ideas, hopefully you'll be able to get logistic regression and also linear regression to work on much larger problems. So that's it for advanced optimization concepts. And in the next and final video on logistic regression, I want to tell you how to take the logistic regression algorithm that you already know about and make it work also on multi-class classification problems.